Hi, so we're going to prove a really awesome result today, which is called the time hierarchy theorem. It's very bold what this is saying, but it's actually really reasonable and not too hard of a proof. So the main idea behind it is if we give you a certain amount of runtime, you can solve a certain set of problems. But if I give you a little bit more runtime, can you actually solve more problems? And the answer for a certain sense of more is yes. So what we want to do is we want to make sure that we can actually prove that. So if I give you, let's say, n time, you can solve a certain set of problems. Then if I give you n squared time, this will tell you that you can actually solve more problems. There are some problems that run in n squared time, but can't be solved in n time, for example. In fact, one thing that we'll show is that you can actually strengthen that to say like n to the 1.01 or 1.00001 time. There are some problems that you can solve in that little itty bitty more runtime than n. And that's what we're going to show. So what do we actually need to be able to prove this? So one thing that we'll need is something called time, let's spell it right, constructibility. So what does this mean? So why do we actually need this? We need this because we want to make sure that if we're going to show that a certain amount of runtime is different than more runtime, then that means I got to find some language that's in the more runtime and not in the less runtime. So how do you actually do that? Well, you got to make sure that it runs in that amount of time in the first place, the bigger guy. But it also differs, whatever machine you made for it, differs from every other machine that runs in the lower guy runtime or less. So time constructibility helps us in that we got to make sure that it actually does run in the bigger runtime. And to do that, we need to update a counter every time we take a transition. So because we want to be different from every other machine, we can't infer what their behavior is. So we need to actually figure out what the runtime is and update a counter. So in order to update the counter, we have to write down the initial amount of runtime that we're allowed to have on the tape. And that's what time constructibility is. Are you actually able to write the thing down on the tape within the time bounds? That's also important. You've got to be able to do it within the time bounds. So we're going to say that t of n, so that's a function, is time constructible. So that's a term, a definition. If given n in unary, although that's not as important. So we're given the number n as input in the unary notation. Then what we're going to output is t of n in big O of t of n time. So it doesn't matter if I take a certain constant more than t of n, as long as I can output it within the actual value. And importantly here, this one's actually important, this one is in binary. It's not important that it's binary specifically, as long as it is some other base than unary. Okay, so the reason for this is we want to be able to store the counter in a very small amount of space. And if you have any base that's 2 binary or bigger, then it's going to be logarithmic in the size. And if you have it in unary, it's equivalent to the size. So in order to make this optimized, we're going to have it be as small as possible. And if I make it any base bigger than 2, it's only going to affect the constant, and that really doesn't matter for this result. Okay, so this result is insensitive to constants in the O notation. But yeah, the idea here is we output the function value in binary in that amount of runtime. So as an example, n squared is constructible because if I give you n in unary, then you can easily output n squared in n squared time. So notice that the number you have to output is the same amount of runtime that you got. And as long as you can do it in less than that time, then we're golden. Cool. Okay, so what does the time hierarchy theorem say? So I'm going to abbreviate it to THT. So it's a time hierarchy theorem. So what this is saying is that we're going to have, for any time constructible function, t, so for any time constructible function t, then what is the crucial bit here? Then we can say that there's some language L that belongs in time of t of n. So remember, time has big O in front of it. So this language runs in some constant times t of n time. And I should say exists here. So there exists a language in this set. And L is not in little o of t of n divided by log t of n time. So I don't have like a capital time here for little o, and this is not actually right as written here. The important thing to convey here is that L runs in constant times t of n time, or has a machine that runs in that amount of time, and L does not have a machine that runs in this amount of runtime. So this log down here, no one knows whether or not that's possible to get removed, and in some sense this is the best known. But the reason that the logs here is that the updating to the counter to make sure that the machine we're trying to be different from doesn't run too long, it takes that amount of runtime. So that's the reason why that's there. If you can improve this, come talk to me. But this is what we're going to prove. Okay. So how do we actually do this? So let's prove this. So how do you actually do this? Well, what we want to do is we want to build a machine that definitely runs in this amount of time and differs from any machine running in the lower guy runtime. So we're going to say that we want to build a Turing machine, let's call it D, such that D runs in big O f event time, and differs from all TMs that run in the lower guy runtime. So little o t of n divided by log t of n time. Okay, so if it differs from all of them, then we're good. So this is the idea behind the proof. It's a proof by diagonalization. So we're going to make sure that this machine D that we make is going to be different than all of the other ones. So in effect, what we're going to do is we're going to simulate some other machine in a certain amount of runtime and then do the opposite of whatever that machine says. And then therefore we must do must be different. And we're going to ensure that D runs in this amount of time, and by definition does not run in this amount of runtime, and it must be different than all other machines that run in this amount of time because it differs from all of them. Okay, so how do we actually construct D here? So D is going to be given some input, let's say W. Then what we want to do is we want to actually construct that counter. So we're going to calculate t of n, where n is the length of W. And we will note, because this works because we've assumed that t is time constructible, and which means it runs in big O of t of n time. So this step runs in big O of t of n time to do that. Okay, and so we haven't exceeded our budget yet. So now what we're going to do is we're going to store a really particular value on the tape. So we're going to store this value. So it's going to be the ceiling of the t of n over log t of n on the tape. Okay, so we're gonna calculate this value, calculate the log of it, and then take the original value divided by the smaller value, and then write that value on the tape and take the ceiling. And so I'm not going to go through the argument, but this one also takes big O of t of n time. In fact, you can actually do it significantly faster, but I'm not going to go through the argument here. Okay, so what we're going to do is we're going to interpret this thing right here as a Turing machine with some input. Okay, so if W is not of the form with some Turing machine, some separator, and some string after the fact. So this thing better encode a Turing machine, and this thing better encode a some string. If it's not of that form, then we're going to reject. The reason for this is that we want to be able to, quote unquote, simulate the machine that's been given to us. So if it doesn't encode a machine with a string, then forget about it. Then we have ran in that amount of runtime, and it's not going to differ from the other machines anyway, so it's not a big deal here. It's just to ensure that we're going to run a machine here. So then what we're going to do is simulate this machine right here, so M, on W. So this input, which was the one that was originally given to us, so this 0 after the fact, we're going to forget about it. It's never going to come back for us. So although it will be useful in the proof here later. So we're going to simulate that machine that the original string encoded on that string itself. So it's kind of reminiscent of the ATM problem, where we're trying to show that this machine is different than all the other ones by simulating it on itself. So effectively, we're going to run M on that particular string W that was given to us up here. And then all that we're going to do is two things. Is we're going to decrement that counter, the one from step 2, for each transition. So for each transition taken on this simulation, subtract 1 from the counter. Then if the counter ever hits 0, then what we're going to do is we're going to reject immediately. Okay, which means that the machine M ran longer than our budget, which is fine. Because we're not trying to be different from the machines that run in too much runtime. We're trying to be different than the machines that run in that little runtime. So if the machine actually did run to completion and we ran within our budget runtime, then we're going to do step 6, and then we're going to output the opposite of what M did. Okay. So if M said accept, we're going to reject, and if M rejected, then we're going to accept. So it's pretty clear that this machine D is going to be different than every other machine that makes to this step down here. And if it makes it to that step, then that means that this machine M ran in that amount of runtime. Okay, so let's write that down. So D is different from every Turing machine that runs in at most T of n divided by log T of n time. Okay. So it's obviously different from that. So one thing that we actually need to be really careful with is because we can't reuse time here. So we need to really be justified in doing each of one of these steps. So the last steps are okay because that just depends on what the machine M does. So we don't know what M is because it's encoded in the string that were given to us, which is arbitrary. So the really hard part here is to be able to do this part right here. It's, oops, meant to do this. It's this part right here. So it's decrementing the counter. So let's actually think about this really carefully. So if we were naive and we had the simulation, let's say right here, and then let's say that like there was a delimiter, and then here's the counter over here, then what we would have to do to update the counter is we do a transition over here, work our way over here, update the counter, and then come back. So if we were not careful, then this will take way longer time than we actually want. This will actually take more than log t of n time. In fact, it may take t of n time. Forget the log. So if we're not careful, then this updating can be not so great. So here's the really awesome idea, is to use a multi-track tape. So the name multi-track is actually kind of a misnomer. So the idea is to have multiple tracks, which is really one tape, but we think of it as having multiple tapes, even though it doesn't actually have multiple tapes. So here's the idea. So we're going to have the simulation occur up here. And what we're going to have right under it, right where we are, is we're going to have the counter stored right there, right under where the tape head is. So then if the tape head, let's say, moves to the right, then we're going to shift the counter over one position. And then if the tape head moves left, we shift the counter left one position. And so why is this better? So, and we have to justify that this actually, you can actually do this first of all, but why does this work? So the counter size here is going, since it's in binary, that was the crucial bit from earlier, since it's in binary, it's going to be the logarithm, or the size of it is the logarithm of the original value that we gave it, which was that t of n divided by log t of n thing. So this is going to be log of, well, big O of, but I'm going to not say that here. So it's going to be log of t of n divided by log t of n. Let's make sure I can write it right. And this log on the bottom is effectively useless. So it's this log t of n at the top that is determining its real size. So this is about log t of n. So the amount of runtime to be able to update the counter is log t of n. And to move the counter one position over takes big O of log of t of n time. To be able to move to the end of the counter and then move it over if necessary, or move it the other way. And so it takes log t of n time to be able to do that. Now, so how do you actually do this in practice? What you do is you increase the alphabet. To be able to actually do this, you increase the alphabet. So what we're going to do is kind of like some of the Sipser problems, which is that each of the characters on the tape encode two different things. So like if there was, let's say, a 0 and a 1 here, like that, then we would have a character that is called 01, and that is one character on the tape. So increasing the alphabet doesn't increase the runtime of the machine, so we're okay, as long as the alphabet size is finite, which it is here. And there's some bounds on how big the alphabet can get. It's not really that important for this discussion. So the important thing is that we increase the alphabet size so that we can effectively have the counter with us underneath where the tape head is. And if the tape head moves one way, we move the counter that way. And so updating the counter, we don't have to move really, really far to update it and then come back. So that's the real purpose of that. Okay, so let's see. So how do we actually make sure that this actually runs in the right runtime? So this this calculation of this takes t of n time. Actually writing this on the tape in terms of that second track, that takes t of n time too. This simulation can take any amount of runtime, but we're going to hit one of these two steps in the lower guy runtime. So it actually, not quite that, but the number of transitions of m taken will take that long. So here, notice that the updating of the counter takes log t of n time. Okay, so it takes log t of n time to update the counter, so the total amount of runtime that's taken for these last bit is going to be the lower guy, so t of n divided by log t of n times log t of n. I'll write that better, I promise. So that's times log t of n, because that's the amount of time it takes to update the counter every single time. And so the total runtime is going to be big O of t of n. So to actually make sure that this is actually going to be a little o of t of n is to actually think of it this way. So let's prove that this language L is not in little o of t of n divided by log t of n time. And effectively what this has to show, so this is equivalent to showing that m runs in that amount of runtime. Because we showed that the machine D that ran in the t of n time, whatever its language was, differs from every machine that runs in that amount of runtime. And what we need to show is that m runs in that amount of runtime because it's different from it. Okay, so let's suppose not. Let's suppose that this is false. So suppose that L really is in that amount of runtime. So suppose that it runs in that little low runtime. Okay, we're gonna find a contradiction at some later point. So what we're gonna have here is that this machine D that we made upstairs runs in, actually I should give a name to this. So let's call this thing, I'm gonna call G of n. So G of n is the little low guy, whatever it is. So D runs in some constant times G of n time. If you follow the argument, it runs in a constant amount of time more than this. Runs in some constant, let's call it C times G of n time. Okay, so what we can infer from the fact that G of n is little low here is that at some point, by definition of little low, this implies that this value, whatever it is less than t of n divided by log t of n for all n at least some number n0. So n0 is the point where it's like these two functions, you gotta decide which one's the bigger and which one's the smaller. So it's this is by definition of little o. So as long as the input n is bigger than this guy, then that's what this means here. Okay, so this guy runs in that amount of runtime, or not that amount of runtime, it's less than this number. Okay, so what are we going to do here? So now what I'm going to do is something really interesting. So consider when the original input W, remember that encoded the machine along with the little extra bit that we threw away. Now it's going to come back to help us show that this machine really can't run in the less runtime. So let's see, we're going to say that we're going to look at W encoding some machine along with the little separator there in a whole bunch of zeros. How many? N0 of them. Okay, So I'm going to consider that string right now. Okay, so what does this mean? So because this amount of runtime is less than the limit that we have, because this machine, this input has length longer than n0, so we have that the length of w is at least n0, but it's actually way more than that, then this means that the machine M will finish on input W. Okay, because that's how we actually constructed the machine before. So M actually will finish W because this input is sufficiently big. We don't know what this number is, but we don't have to construct the language specifically. We just have to know that there is a constant n0 for this language, and we know that because we're supposing that it runs in the little o runtime. So since M will finish on input W, then that means that the machine D will do the opposite. So D will do the opposite, which will contradict the fact that D has language L, but since we did the opposite, we disagreed from this other machine which ran in that amount of runtime. And so therefore, this language could not have been in this amount of runtime. So this thing is a contradiction. And so therefore, we have proven that this language is not in little o of the smaller guy runtime, and we proved it's in the bigger guy runtime. Now there's obviously a gap between them, a logarithmic factor gap here, but effectively this will show that for sufficiently far apart runtimes, you will have some language that runs in one and not the other. So let me tell you some implications. So one of them is like time of n is contained strictly within, let's say, time of n squared, because n is asymptotically less than n squared divided by log n. Okay, we can't say anything about n versus n log n, because if we divide the log out, then we got to find a function asymptotically smaller than n, but also be equal to n. So that's not going to fly for us. One thing that you can show here is that polynomial time is not equal to exponential time, because any polynomial that you want is going to be less than any exponential that you want. And this will get us something really interesting, in that we'll eventually see some containments within each of these between p and x time, which would imply that one of those containments is strict. But one thing that at this point, as the recording of this video, we do not know if any of them are actually strict. So, which is kind of interesting. You know that one of them is strict, but you don't know which one it actually is. We believe all of them are, but we don't know which one specifically. So that was the time hierarchy theorem. I know this was a long video, but it deserves a really long video because it's such an awesome result. Leave comments about the time hierarchy theorem into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.